Well, I see I got my two regulars, Conrad and Alex. If things follow suit, or at least normal behavior, maybe I should say, Boyke should be along in another 10 or 15 minutes, and I haven't seen. Oh, oh, look. Well, hello, Dugan. Fancy meeting you here. Uh, okay, so let's see. Due to my low internet quality, uh, I'm turning all the videos off. And due to the fact that it tends to do some serious feedback loops, I've turned the sound off. You can turn it on when needed. This unit is semiconductors. I've gotten, before I get to that though, I have gotten most of your tests. I think that Alex, last I checked, I haven't checked this morning yet. I'm missing some worksheets from you. And Dugan, I'm missing some stuff from you. I think that Conrad and Gwen have everything done. Now, this unit is semiconductors. There is a little bit of notes, just a little bit. Mostly, this is supposed to be assembling kits. Not 100% sure what's going to happen with the kits, and if it doesn't happen with the kits, then I don't know what's going on. I have the kits, except we've used the kits 2 or 3 years, and several of the components have been destroyed. I mean, they look fine, but they're non-functional. There are some things that if you put them in wrong, or if you put them in without the right resistor, it burns them out. You can't really tell by looking at they're burnt out. They just don't work. So I ordered replacement parts, uh, but I haven't got notification that they've been sent out yet. And so I don't know if that company is functioning under, it's from Florida, and I think Florida has a fair amount of the COVID. So I don't know if that company is functioning now or what. And if the parts don't come, I don't know how I'm going to work that. Maybe I'll have to go into school and sort through all of the kits and see if I can find enough parts for 4 kits. I don't know. What we will do, if and when I get the kits out, is basically we'll have a Zoom meeting and you can work on them and show me when something's functional. Now, the bad news about that is it's not something that you can do too much outside of the Zoom time because I won't be there for you to show it to me. All right, so anyway, semiconductors. Semiconductors, semi means like part or partial. So we talk about semis on the road, but semi is short for semi truck because the truck has 2 pieces, the tractor which pulls it and the trailer which is pulled. So each of those is only part of a truck. That's why we call them semi trucks. Semi means partial. So semiconductors are elements which conduct electricity, but not super well. On the periodic table, I had a periodic table. It's another window here. So on the periodic table, the semiconductors are the metalloids, which are in the kind of dark yellow, almost orangey boxes. These are the metalloids. The semiconductors are from this group. Remember, the metals conduct electricity freely. The nonmetals don't conduct electricity. And in the middle, we've got the metalloids, which conduct electricity, but not super well. Now, all of the metalloids are not used for semiconductors, at least not in electronics. The most common of the semiconductors used in electronics are silicon or silicon. Silicon is a form of silicon. Did I say that right? Silicone is a form of silicon. So these two right here, silicon, number 14, and germanium, number 32, are the most commonly used semiconductors of the metalloids. Now, there are two types of semiconductors, and these terms may not lay out in the notes as parallelly as you might think off the top of your head that they would, but it'll make sense here. So there are intrinsic and extrinsic semiconductors. If something is intrinsic, it means it is built into something. It is a part of something. It's just an automatic goes together kind of thing. Extrinsic means that it comes someplace from the outside. So I think you talked about, if you took psychology, I think you talked about intrinsic motivation and extrinsic motivation. Intrinsic would be, if you have it in a certain area, just the desire to excel, the drive to excel. Extrinsic would be like, you don't have the drive to excel, so your parents say, I'll give you $10 if you get an A on this test or something like that. So intrinsic semiconductors just automatically are semiconductors. The problem is that they conduct as a function of heat. They have a very small conductivity and a high resistance. Well, the problem is things with high resistance tend to heat up quite a bit and sometimes quickly when a current flows through them. And if their conductivity is a function of heat, that means that their conductivity is going to change as you use them. Well, that's a problem, because if you built electronics that changed with heat, either they wouldn't work when you first turned them on because they would not have warmed up, or they wouldn't work once they were warmed up because they were too hot. And heat still is a problem with semiconductors. That's why your computer, for example, probably has a fan in it. Almost certainly has a fan, but I guess they've got some fairly low heat processors now. So to get around that, we dope the semiconductors. Now, modern slang and the term dope, no, I'm not saying that right. The term doped in modern slang does not give a really accurate idea of what this term means. So if I say dope, people automatically think of drugs, or maybe a specific kind of drug, because dope has been a slang for drugs for so long that most people don't know it ever meant anything else. But in fact, in the days before synthetics, nylon and polypropylene and so on, when we used canvas for tarps and covers and tents, canvas is a heavy, I believe, cotton fabric. And it's very tight, but it's not waterproof. So if you went back to, let's say, the Civil War, the troops either side would set up camp and they would set up their tents. And if it rained, a lot of the rain would run off, but some of the rain would soak through. And the wetter the canvas got, the more rain would soak through. And no one likes sleeping with water dripping in from the tent. So they would paint this gooey, sticky stuff onto the tent to make it waterproof. That gooey, sticky stuff that they painted onto the tent was called dope. And they were doping the tent, doping the canvas to make it waterproof. This term actually made it into my era. My dad used to talk about gunky stuff that he needed to put on something dope. So before there was Teflon tape for pipe joints, you would put this gooey gunk on the pipe threads, and my dad would call that the pipe dope. So basically, dope used to be something that you added to a tent or added to a pipe thread to make it to seal up. But it was added. See, that's the thing. It was something added. And even though semiconductors haven't been in common use back into the 40s and 50s, they were being developed in the 40s and 50s. And that was before dope meant drugs. And so dope simply meant something that was added. So the intrinsic semiconductors, which is what we use now, the extrinsic, are semiconductors which have had their conductivity increased by adding dopants. And the dopants were other atoms, in other words, of other elements, with extra what they call electrons or electrons holes. And notice that holes is in quotes. What holes meant was they had the ability to take in extra electrons. So basically, extrinsic conductors are semiconductors that have had something added to make them either more likely to give off electrons or more likely to take on electrons. And these extrinsic conductors are pretty much what electronics are based on overall. Yep, I was pretty much right. All right, so we have basically two types of extrinsic conductors, doped semiconductors. We've got the N-type and the P-type. I think, but I'm not 100% positive that N refers to negative and P refers to positive, but at least it's a good way to remember it, because N-type give electrons, which extra electrons would be negative, and P-type accept electrons, or in other words, they're said to have the electron holes, and taking electrons, something that can take electrons is positive. Once it takes the electrons, it's not positive anymore. But N-type and P-type are the two kinds. So we've got arsenic, which is a common but not the only dopant in N-type. And I guess I need to shrink this down here. Arsenic is itself a semiconductor right here, but it's not the main semiconductor, main element in the mix. And gallium, you know, like a large sailing ship, no, wait. Gallium is actually the place on the ship where they cook and serve food. I know, but I didn't want you to feel bad about, you know, not being in class. Gallium is right here. So germanium, arsenic's on the non-metal side, gallium's on the metal side. And they're not the only dopants, they're some of the common ones. So basically then, the major electronic components are made by taking N-type and P-type semiconductors and putting them together in different combinations to accomplish different things. And I am not going to go into huge detail on I'm not going to go into huge detail on all of the different kind of electronic devices, and maybe devices is not the best choice of words because you might think of an electronic device given modern usage as like a cell phone or something. So by devices, we're talking about the components. Talking about the parts that make up the cell phone or the computer or whatever. By the way, we've gotten these parts so terribly miniaturized that a lot of them you cannot even pick out on a device like a cell phone. Some of them you can, but a lot of them are several parts combined and you can't pick out one or the other, one component or the other. All right, so first on our list, and this is the only one we'll talk about today, is diodes. Di, D-I, meaning two. So diodes are two pieces, joined region of a P-type and an N-type semiconductor. The schematic symbol, we did schematics and electricity a little bit, and when you do the kits, you will be seeing some of these schematics in the instructions. And if you never get the schematics, there is also pictures of the actual device, of the actual component. No, I don't want you to restart now. So basically, you put an N-type together and a P-type together, and they don't really look like this. They frequently are little cylinders, but they don't have one labeled N and one labeled P. And you can put them either way. You can put them and put them. Where are we talking about putting them? In a device. The holes in a device. So you've got a circuit board and you've got two holes, and you're going to put, you're going to put this into one hole and solder it, and the other wire into the other hole and solder it, and you can put them in either P and N or N and P, but they don't work the same way depending on how you put them in. So in reverse bias, the negative electron source is attached to the P-type. So negative, let's see, negative is attached to P and positive is attached to N. That would be reverse bias. In reverse bias, they do not conduct electricity hardly at all. They act as a very large resistor. In forward bias, you are putting the positive source with the P-type, like so, and the negative source, like so. If I can get this to not erase everything like that. And in that case, so positive attached to the P and then negative attached to the N. In that case, they act as a conductor. So in one direction, these resist electricity flow, electron flow, and in the other direction, they allow electron flow. So I don't know, let's see, this is 2020, probably 15 or 18 years ago. Okay, so you were either little kids or not born. Back before iPods, back before cloud music and so on, about 15 to 20 year ago range, the high tech, if you will, or the state of the art personal music was a little personal CD player, battery operated, or you could plug it in with an adapter, like you can plug in your cell phone with an adapter. And a kid had a CD player that would work plugged. Let's see, it would work plugged in, but it would not work on batteries. And so he brought it to me to fix. And I was pretty sure I couldn't fix it, but he begged and pleaded, so I opened it up anyway. And I started looking at, I got lucky. I started tracing the battery circuit on the motherboard, and the very first thing on the circuit was a diode. And I thought, I think that's in backwards. Now, this was not miniaturized, so small that I couldn't deal with it. So I took my soldering iron and removed the diode and turned it 180 degrees and put it back in and soldered it. And just like that, the player worked on batteries. I got lucky. If it had been one of those teeny tiny components, I never would have found it. But the point is that in one direction, this blocks electron flow, and it was in backwards, so it was blocking electron flow from the batteries. In the other direction, it allows electron flow. That's basically what diodes do. So diodes, therefore, can be used to rectify an alternating current. Rectify means change to DC, except it's not a true DC, because if AC goes like this, and let's say AC goes like this, and the diode only lets one direction. Let's say the diode only lets this part of the electricity through, the part above the x-axis, the positive part, let's say. So what happens is the diode cuts off all of this part of the electricity. So only the part above the x-axis, so to speak, is allowed to flow. Well, that's not true DC. True DC would be steady wink of electricity, and this is wink, 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 60 cycle per second, very fast, but it's only 1/60th, I mean, 1/2 of the time the electricity is flowing. Now, the surges are, like I just said, 1/60th of a second, so they're so close together that for most devices, it still works like DC, but it's not true DC. Diodes also, whoops, got to change color back. If I underline it in white, you're never going to see it. Diodes also will not conduct until forward voltage reaches a certain point. Usually it's around 0.6 volts. So because of that, they can be used to make a device only function within certain voltage parameters. There's several kinds of diodes, and I'm sure this is not an exhaustive list. Small signal diodes transform low current AC to DC. They can be used to detect radio signals, absorb voltage spikes, multiply a voltage. And most of us have never really heard of small signal diodes. We have heard of light emitting diodes, or LEDs. They are designed to emit light in forward bias, but I do want you to notice this. Okay, they emit light in forward bias, but all diodes emit some form of electromagnetic radiation. So some it's light, some it's ultraviolet light, some it's radio waves. They all emit some kind of electromagnetic radiation. Photodiodes are designed to detect light. So like if you've got a photo sensor, a light that automatically comes on when it's dark, or if you have your cell phone set to automatically lower the screen brightness in dark light, they're using a photodiode. But again, all diodes respond to light. Some of them, the response is not noticeable to us. Photodiodes are the ones that respond well enough that they can be used actually to detect light. Zener diodes operate only at specific voltage, so they can be voltage sensitive switches. And I'm sure there's others, but they're some of the main ones. So that's as far as I wanted to get today. Tomorrow we will talk about transistors. Hopefully, it's been several days since I ordered those parts. Hopefully they'll show up sometime in the near future. Otherwise, as I said earlier, we'll have to figure out what to do. Were there any questions? All right, then I'll let you go. Make sure that you get anything made up that you may not have done. See you later.